Hey everyone, in this video we're going to go over section 3.2, the product rule. So if we have two differentiable functions, f and g, what we have so far is we know that the derivative of the product of the sum of f and g is equal to the derivative, or is equal to the sum of the derivatives. And we have the derivative of the difference equals the difference of the derivatives. So one might assume that the derivative with regards to x of the product, f and g, is equal to the product of the derivatives. But that actually isn't true. If we call, say, f of x, x squared, and we call g of x, x, well, the derivative with regards to x of f is equal to 2x, and the derivative with regards to x of x is equal to 1, but the derivative with regards to x of f and g is equal to the derivative with regards to x of x squared times x, which is equal to the derivative with regards to x of x cubed, which is equal to 3x squared. Well, 3x squared is definitely not the same as f prime of x times g prime of x. So we need to come up with a rule that allows us to take the derivative of the product of functions, similar to the way we developed rules that help us take the derivative of the sum of functions. So I'm going to do a geometric proof of the product rule, and we're going to need a picture. So for the product rule, for any value of x, we can think of f of x and g of x as the area of a rectangle. We've got a base times a height, so let's say we have this rectangle. I'll call this side length f of x, and I'll call this side length g of x. And if we want to figure out what the rate of change is of the product of f of x and g of x, well, that means we're interested in how this area is changing if we increase f of x by some amount. And g of x by some amount. So, in other words, we want to see how the area changes as we increase f of x to some f of x plus h, and g of x to some g of x plus h. And that'll be that entire new side length. Now, for the sake of argument, we'll need this in a second. So this little region, this side length, well, it's going to be this whole side length, f of x plus h, minus this side length, minus f of x. Similarly, this side length, and I've ran out of space over here, so I'm going to draw it over here. This side length is this new height, g of x plus h, minus the old height, minus g of x. So, what we have here is we are interested in how much this area is changing. The area of this region changes as we let the value of x vary a small amount, or as we go from this shaded region to this shaded region. Oh no. I appear to be out of a different color of ink. I will be right back. There we go, sorry about that. like I was saying, we want to see how the area is changing as f of x goes to f of x plus h and g of x goes to g of x plus h, or we want to see the change in area from this black region to this region I'm now going to shade in green. All of that. We want to see the change in that area. Or, if all we do is care about the change in the area, what we are interested in is we want to see how the product of x plus h and g of x plus h differs from f of x and g of x. That would give us just this region here. Well, this actually gets kind of long, so I'm going to rewrite this on this page, and we're going to proceed in landscape mode. So we're trying to investigate the difference in these areas, or we want to explore f of x plus h times g of x plus h minus f of x times g of x. Well, this area, that's the same thing as, well, we have this square, or this rectangle. This tall rectangle has a height, or we'll say has a width of f of x plus h minus f of x. That's its width, and its height is g of x plus h. And we have this rectangle whose width is g of x plus h minus g of x. Times its length, which is f of x plus h. But if we add this area to this area, we have double counted this area. So we will have to subtract this little square, which has area g of x plus h minus g of x times f of x plus h minus f of x. So all we've said by this equation is that this L-shaped area, the difference between the big area and the little area, is equal to that rectangle plus that rectangle minus that square. Perfect. So now, what I want to do, or what we're going to do, is we're actually going to divide both sides of this equation by an h. Both sides are equal, so both sides, when divided by h, have to be equal. And now I'm just going to rewrite this one step lower, because our next step is going to be, we're going to take the limit of both sides as h goes to 0. So we care about the limit as h goes to 0 of f of x plus h, g of x plus h minus f of x times g of x all over h. And that has to be equal to the limit as h goes to 0 of f of x plus h minus f of x all times g of x plus h divided by h. And then to that we'll add the limit as h goes to 0 of g of x plus h minus g of x all times f of x plus h all divided by h And then finally, we're going to subtract the limit as h goes to 0 of g of x plus h minus g of x times f of x plus h minus f of x all over h. Perfect. These two were equal, so when we divided by h they were equal, and when we take the limit as h of both sides, and as we take the limit as h goes to 0, the limit of both sides will be equal. Well, if you look, what we have on the left is we have the definition of the derivative of f of x times g of x. By the limit definition of a derivative, this left-hand side reduces to the derivative with regards to x of the product of f of x times g of x. And that's just limit definition. Similarly, if you take a look at what we have here, we have g of x plus h times the limit as h goes to 0 of f of x plus h minus f of x all over h. So this becomes, this part becomes the derivative f prime of x, and then as h goes to 0, g of x plus h just becomes g of x. Now we're going to add, the same but opposite is true over here. What we have is the limit as h goes to 0 of g of x plus h minus g of x all over h, and all that is being times by f of x plus h. Well, the limit as h goes to 0 of g of x plus h minus g of x all over h is equal to g prime of x times f of x plus h as h goes to 0 is just a f of x. And now we have this part down here. Well, we've got two options. We can either group this h with the g of x's, or we could group that h with the f of x's. If we group the h with the g of x's, we get minus, well, we get g prime of x, but as h goes to 0, f of x plus h minus f of x becomes 0, and that term drops. And we go, okay, well there was another way you could have grouped it. We could have gone through all of these steps, and we would have gotten the derivative with regards to x of the product of f of x and g of x is equal to f prime of x g of x plus g prime of x f of x. And now, let's say we group that h with the f of x's. Well, that would give us minus. We would get the derivative of f prime of x, but once again, now we're taking the limit as h goes to 0 of g of x plus h minus g of x. That too would be 0. So it doesn't matter how we address the back term, both of them are going to give the same result. What we know is this, what our product rule says, and we'll skip over the derivation. I'll never ask you guys for that, I just like to show you where it comes from. That wasn't used. We get the product rule. Saying that if we've got two differentiable functions f of x and g of x, the derivative with regards to x of their product is equal to, and there's a couple different ways of writing it. I like the prime notation, f prime of x, g of x, plus g prime of x, f of x. You could also say, and I've switched notation here, we could say this is also equal to the derivative with regards to x of f of x, that times g of x, plus the derivative with regards to x of g of x, times f of x. I like this top one. And remember, you can multiply in any order you want to. Some books will put the g of x first and the f prime of x second. Same thing over here. You can multiply in any order you want to. So we could switch the position of f of x and g prime of x. You can also add in any order you want to. So we could take this term and move it over here, and this term and move it over here. You can add or multiply in any order you want to, and there's a couple different ways of saying the exact same thing, f prime or d dx. So that's why you might see a big variation in the way this gets written in our book, online. A lot of different ways to say the same thing. But what I remember is the derivative of the product is equal to the derivative of the first times the second plus the second, the derivative of the second times the first. This is what I say in my mind pretty much every time I use the product rule. The derivative of the first times the second is equal to the derivative of the second times the first. That's super easy for me to memorize. I memorized that back when I was in Calc 1, and I have used it, like I said, for taking the derivative of any product ever since. Examples. Cool. So our example. That's good. That's right there. And what I actually want to do, let's keep this up. There's our product rule. I need another piece of paper. And let's do some examples. So what we have is if f of x is equal to x e to the x. We want to find f prime of x. So what the book goes through, and the book will call f of x x e to the x, and then they'll define a small f of x and call it x, and they'll define a small g of x and they'll call it e to the x, because after all we've got two functions here being multiplied together. We need f prime of x. F prime of x is equal to 1, and g prime of x is equal to e to the x. And we have a formula. We know that the derivative with regards to x of that capital F of x, well, that's equal to the derivative with regards to x of the product of f of x and g of x. That's equal to the derivative of your first times your second plus the derivative of your second times the first. So we have all the pieces we already need. This is just plug and chug. What this shows is that the derivative with regards to x of x e to the x is equal to the derivative of our first times our second plus the derivative of our second times our first. So at this point we can simplify a little bit. We get an e to the x plus an x e to the x as our final answer. There's a lot of different ways you can write this. My primary concern is grading your guys' calculus. The book, in this example, goes through, factors out an e to the x, and calls this 1 plus x. There is definitely value in doing this, but for the sake of doing calculus, all the calculus all the calculus really stopped at this step, and I want you guys to simplify to about that step. Some problems it might be convenient to take this further, but you guys can stop right here. But let's go one step further. Let's come up with the formula for the nth derivative of x e to the x. If you guys get tasked with finding an nth derivative, what you should do is you should take the derivative again and again and again until you see a pattern. So, for that, we'll say the derivative with regards to x of x e to the x is equal to the derivative of your first times your second plus your first times the derivative of your second, which is equal to e to the x plus x e to the x. Our second derivative, the second derivative with regards to x is equal to the derivative with regards to x of e to the x plus x e to the x. Well, that's equal to derivative of e to the x is just e to the x plus the derivative of your first times your second plus your first times the derivative of your second. That's going to be equal to e to the x plus e to the x plus x e to the x, or that is 2e to the x plus x e to the x. Well, let's calculate the derivative again. The derivative, or the third derivative, with regards to x, and I forgot to put a 2 there. Well, that's going to be equal to the derivative with regards to x of our second derivative, 2e to the x plus x e to the x. That's going to be equal to derivatives. They distribute across addition, and constants can be pulled out. The derivative of 2e to the x is just 2e to the x plus the derivative of our first times our second plus our first times the derivative of our second, which is 2e to the x plus e to the x plus x e to the x, or 3e to the x plus x e to the x. Technically, we would need to go through what mathematicians call a proof by induction to finish this problem, but if you guys start to notice the pattern, how when we took the first derivative, there was 1e to the x and an xe to the x. When we took the second derivative, there were 2e to the x's and an xe to the x. And when we took the third derivative, there were 3e to the x's and then an xe to the x. Well, if that pattern continues, I think it's a fair assumption to assume that the nth derivative of xe to the x is equal to n e to the x plus xe to the x. So, so the book, they go through and they call this e to the x times n plus x. Like I said, there is definitely some value in condensing everything down. Typically in a math class you're told to always simplify, always simplify. In this problem, there's no calculus going from this step to this step. If this is a logical step for your work, go ahead and take it, but you don't have to try and condense everything down. And for the most part, unless otherwise instructed, I would prefer you guys to leave your answers like this. If you leave your answers like this, that demonstrates that you have done all the calculus correctly. And I'll give you full credit for it. But if you try and simplify your answer beyond what is necessary, and you made a mistake, I'll grade your final answer. So even if all your calculus is correct, I would still have to mark you wrong if you made an algebra mistake. you can stop at the step where you're done with the calculus. Aside from simple little simplifications like 1 times e to the x, we replace that with an e to the x. That's really cleaning up your work. Grouping these two e to the x's to 2 e to the x, that's really cleaning up your work. But starting to factor things out, that's a little above and beyond. Let me start recording again and we'll do a couple more examples. Okay, so example 2. It says that f of t is equal to the square root of t times a plus bt. And we want to find f prime of t. Okay? Well, like I said, we've got these two functions. That's multiplication. And what I'm going to do is I'm going to call this big function actually capital F of t, and that's equal to the square root of t times a plus bt, and I'm going to call little f of t the square root of t, and I'm going to call g of t a plus bt. Well, we need f prime of t. Derivatives are much easier when we convert all square roots or all roots to exponents. And that's still f of t. And f prime of t, by our power rule, this power comes down. We get 1/2 of t, and then we subtract 1 from the exponent to the negative 1/2. G prime of t, we're taking the derivative with regards to t. That a is a constant, so that equals 0. I'll write this here. G prime of t is equal to 0 plus b is a constant. B times t, that's like taking the derivative of a 3x. B plus t, or the derivative of b times t, would just be b. And so we're left with g prime of t being equal to b. Well, the derivative with regards to t of this thing, of the square root of t times a plus bt, is equal to the derivative of our first times our second plus our first times the derivative of our second. So at this step, I can call this, the only thing I would do is I would call that 1/2 of a t to a negative 1/2 times an a plus a bt plus bt to the 1/2. You could also go through and call this a plus bt all over 2t square rooted plus b square roots of t. I want you to stop at this point. There is no point in further simplifying to here. If you're checking your answers in the back of the book, however, the book may continue to simplify to a later step. So don't be surprised if you have to algebraically manipulate your answer to get to the answer in the back of the book. Let's do another example. We'll keep the ball rolling. We'll say example 3. We'll call, let's say we have this capital F of x, and it's equal to the square root of x times a g of x. And we also know that g of 4 is equal to 2. G prime of 4 is equal to 3. And f prime of 4 is equal to, and we have to find f prime of 4. F of x, g, perfect. Well, to find capital F prime of 4, that's a capital F, we know that the derivative with regards to x of a capital F of x is equal to the derivative with regards to x of a little f of x times a little g of x, which is equal to the derivative of your first times your second plus your first times the derivative of your second. That's supposed to be an x and not a t. So that means the derivative with regards to x of f of 3 g of 3, not 3, I'm sorry, I should be writing 4. I saw a lot of 3's floating around. That means f prime of 4, which is equal to the derivative with regards to x of f of 4, g of 4, is equal to the derivative of your first, times your second, plus your first times the derivative of your second, g prime of 4. Well, right here, we've got the square root of x. Our little f of x is equal to the square root of x, which is equal to x to the 1/2. And f prime of x is going to be equal to 1/2 of an x to a negative 1/2. Now we have all of the information that we need. F prime of 4, the thing that we're after, is going to be equal to little f prime of 4, 1/2 of 4 to the negative 1/2 times g of 4. G of 4 is equal to 2, plus f of 4. F of 4 is going to be 4 to the 1/2 times g of 4, times g prime of 4, I'm sorry, and g prime of 4 is 3. Simplifying, it might help to rewrite this. This is 1 over 2 times the square root of 4 times 2 plus the square root of 4 times 3. Oh, that 2 is going to cancel out with that 2, and we're left with 1 over the square root of 4 is 1/2, plus the square root of 4 is equal to 2. 2 times 3 is 6, and we get 13 halves. So, just by given the values of g's, we were able to calculate the value of this derivative. For our product rule, we have the derivative of the product is equal to the derivative of the first times the second plus the first times the derivative of the second. Remember, you can multiply or add in any order you want to, and I think I've been saying it more in that order. So, yeah, we'll do some more examples of these. I just want to make sure before we shift gears and do something else, I'll be able to give you a couple good examples. Let me give you one more. Gotta find my stash of paper. There we go. So, let me do this. Cool, so one more example. This is actually problem 4, number 4, out of the homework section. We want to calculate the derivative. We want to calculate the derivative of a product. Good thing there's a rule we can use to help calculate the derivative of a product. We'll use the product rule. What the product rule says is that the derivative of g of x is equal to the derivative of the first, and I'll write it a different way this time. The derivative of the first times the second plus your first, times the derivative of your second. So we get that just from the definition of the product rule. The derivative of the product is equal to the derivative of your first times your second plus your first times the derivative of your second. Well, the derivative, and I'll rewrite this, we'll say that that's equal to the derivative with regards to x of x plus 2, x to the 1/2, e to the x, plus x plus 2, and I can leave that one as the square root of x, times the derivative with regards to x of e to the x. I have a rewrite stage, I have an algebra stage, then I'm going to have a calculus stage. I could have performed some calculus at this stage, I just don't like to mix my flavors of math, if that makes any sense. Performing this derivative, and the only thing we're taking the derivative of is this chunk in the front, the derivative of the first. That's going to be equal to the derivative of x is 1 plus 2 times the derivative of x to the 1/2. Well, this is our power rule. 1/2 is going to fall down and we'll get 1/2 of x to the negative 1/2. We'll clean this part up in a bit. Times our second, e to the x, plus our first, x plus 2 square roots of x, times the derivative of our second, which is just e to the x. So at this stage all the calculus is done, but simple simplifications like 2 times 1/2 I want you to do. This is going to be equal to 1, plus 2 times 1/2 will simplify to a 1, and we're left with an x to the negative 1/2 times an e to the x, plus, and we don't really have to mess with this, x plus 2 square roots of x times e to the x. And I know I have it written over here, but I'll say that the derivative of the product is equal to the derivative of the first times the second plus the first times the derivative of the second. Derivative of the product is equal to the derivative of the first times the second plus the first times the derivative of the second. By first and second, we're taking the product of two functions here. The first is the one that comes first, and the second is the one that comes second. You can multiply in any order you want to, you can add in any order you want to. That's why this kind of got switched around at the last, or got switched around. But the idea is the same. You take the derivative of one and the other one the way it is, and you add it to the derivative of the other times the way the first one was the way it is. Well, I said something very specific a moment ago. I said that we're taking the derivative of a product, and thankfully there's a rule that helps us take derivatives of products. Well, we also have a rule for quotients too. This is going to be the quotient rule. And really what we're trying to do is we're going to try and take the derivative with regards to x of the quotient of two functions. And by definition, this is going to be equal to the limit, as h goes off to 0, of f of x plus h divided by g of x plus h minus f of x divided by g of x, all divided by an h, by definition. So I'm going to put this numerator on a common denominator, and dividing by h is the same as multiplying by 1 over h. So doing some algebra, limit, as h goes off to 0, like I said, dividing by h is like multiplying everything by 1 over h. This part isn't necessary, I just don't like compound fractions. Putting everything on a common denominator, we get g of x times f of x plus h minus f of x times g of x plus h, all over n x g of x times a g of x plus h. Excuse me. Now, You can multiply in any order you want to. So I'm going to take this g of x plus h, and I'm going to move it out. I'm going to take my h and I'm going to put it right there. Really, I moved the h to the wrong spot at this step, but you're free to multiply in any order you want to. Another thing we're going to do is right here, we're going to add 0. We're going to add 0 in a clever way. What we're going to do is we're going to subtract an f of x, g of x, and then we're going to add it back very quickly, as to not change the value in the numerator. So, and because this gets long, we're going to call this the limit as h goes off to 0. Now what we have is I'm going to call this 1 over g of x times a g of x plus h. We're just moving that out front, times g of x times f of x plus h minus f of x g of x plus f of x g of x minus f of x g of x plus h all over h. These two switched places, and by these two I mean these two. And we subtracted f of x g of x and added f of x g of x. Now what we're going to do is we have this g of x and we have that g of x. We're going to factor it out. And we have an f of x here and an f of x here. We're going to factor those out too. It's equal to that. This is equal to the limit as h goes off to 0 of 1 over g of x plus h times g of x times an f of x plus h minus f of x. Then we're going to factor out that f of x times a g of x minus a g of x plus h. And all this is divided by an h. Okay, and we're close. This looks like the definition of a derivative, and these two need to switch. Well, if I can factor out a minus sign from both of these and turn this into a negative g of, I can turn this into a negative g of x plus g of x plus h. By factoring out a minus sign out of a positive, we get a negative, and by factoring that minus sign out of a negative, we get a positive. In the next step, we're going to change the order of these, and this plus sign and that minus sign are going to combine and turn into a minus sign. By that, I mean, for our next step, we're going to take a limit as h goes off to 0 of 1 over g of x times g of x plus h times a g of x times a f of x plus h minus f of x all over h. And like I said, that plus sign, we have changed this into, and I'll write it like this, plus f of x times negative 1 times g of x plus h minus g of x all over h. So limit h goes off to 0 of, there's nothing keeping h from being 0 in the denominator here. So when we let h go to 0, this becomes 1 over g of x times g of x, which is 1 over g of x squared, times, if you look here, we get a g of x, and f of x plus h minus f of x over h as h goes to 0 is the derivative of f of x. This minus sign will come out front and we'll get minus, we have this f of x, times a limit as h goes to 0 of g of x plus h minus g of x all over h, g prime of x. And we have evaluated that limit at this point. So, if we write this in a nice condensed form, what we get for the quotient rule is that the derivative with regards to x of f of x divided by a g of x is equal to g of x, f prime of x, minus f of x, g prime of x, all over g of x squared. When I was in calculus, my teacher said low d high minus high d low all over low low. And that's what we have up here. We have the derivative with regards to x of f of x divided by g of x being equal to low d high minus high d low all over low low. Like I said, I have that memorized. As I was writing that, I was saying that in my head. I always think of that when I go and do these. That's page 1, that's page 2. We have gotten to page 3. So let's do example 4 on page 3 of my notes. If y is equal to x squared plus x minus 2 divided by x cubed plus 6, well, what is y prime? We're going to use the quotient rule. And I'm going to use this notation right here. Y prime is equal to low x cubed plus 6 times the derivative of our top minus our top times the derivative with regards to x of our bottom all over our denominator squared. Perfect. Now we have to do these derivatives. This is equal to x cubed plus 6 times the derivative with regards to x of x squared plus x minus 2. Derivative of x squared is 2x. Derivative of x is 1. Derivative of 2 is a constant, minus x squared plus x minus 2 times the derivative of x cubed is a 3x squared plus the derivative of 6 is 0, all divided by the denominator squared. X cubed plus 6 quantity squared and stop. You don't have to multiply that all out. You don't have to multiply that all out, and you don't have to gather like terms. Because when I go through and I grade your work, I'm going to be looking for this step. At this step, you have done all the calculus in this problem, and everything that follows is going to just be algebra. Stop right here. We combined it. There weren't any fractions. If there were any fractions, we could have simplified. If you want to, you could call this 3x squared times that thing. I'm aware you can multiply in any order you want to, so I don't really care if you put the 3 over there or the x squared over there and the 3 on the back. Algebraically equivalent answers. But we used the quotient rule, which I've somehow lost. Oh, right there, I'm sorry. We used the quotient rule, just kind of plugged and shoved, filled everything out where it went, and then we went through and took our derivatives. Let's do another example. I'm really going to lose the quotient rule now. EX5. We want to find the equation of the tangent line, or of the line tangent to y is equal to e to the x divided by 1 plus x squared at 1 half of e. 1 half of e, yes. Okay. Equation of tangent line. Lines, they need a point and they need a slope. The point was given to us, the slope is ours to discover. Well, the slope of the tangent line of this function is given by the derivative of this function evaluated at that point. So we need a y prime. That's going to be equal to low d high minus high d low all over low low. So this is a skeleton for our derivative. If you correctly get to that step, I'll give you points. This is I don't see your guys' work, and I don't like that. I like to look at my students' work because I'm concerned with how you guys do this. This in a normal class setting would be worth honestly a majority of the points. Simplifying, derivative of e to the x is e to the x minus e to the x times the derivative of 1 is 0 plus the derivative of x squared is 2x all over 1 plus x squared quantity squared. And if we want to know the slope when x is equal to 1, well, we can call this thing, you can think of it as f prime of a. The slope at this point, where we have an a f of a, is equal to 1 plus a is 1 squared, e to the 1 minus e to the 1, 2 times 1, all divided by 1 plus 1 squared squared. And that's, I'm sorry, that's not a anymore, that should be a 1. F prime of 1 is equal to that thing. Well, that's going to be equal to 1 plus 1 squared is 2, e to the 1 I'm just going to call e, minus 2 times 1 is 2, times e is 2e, all over 1 plus 1 squared is 2, squared is 4. But 2 e's take away 2 e's gives us no e's, and no e's divided by 4 is 0. So what we have found is we actually have a horizontal tangent line at the point 1, 1 half of e. Well, we still need to answer the problem, answer the question. We need to find an equation of a tangent line. Well, y minus f of a, 1 half of e, is equal to our slope, 0, times x minus 1. Anything times 0 is equal to 0. Any number times 0 is equal to 0. And we're left with y minus 1 half of an e is equal to 0, or y is equal to 1 half of e. Perfect. It's what we expect. When y is equal to a number, we have a horizontal line. Our slope was 0, we knew we had a horizontal line. Really taking derivatives, this is something that we've done countless times. Find the equation of tangent lines. The only thing that changes is the method we use to go through and find the slope of the tangent line. Coincidentally, this one was 0. But for the quotient rule, low d high minus high d low all over low low. Yeah, that's about it. Let me go through and say this, maybe give you 1 or 2 more examples. When I was in calculus, I kind of had a white knuckle approach to calculus. If you told me to take the derivative with regards to x of 3x squared plus 2 times the square root of x all over x I would do it. I would do exactly what we've been doing here. I would rewrite this thing, call that fine. That's the derivative with regards to x of 3x squared plus 2, times x, again, to the 1/2, all divided by x. And then I'd do our quotient rule. That's equal to low d high minus high d low all over low low. And I would have gone through, well, x stays the same. The derivative of 3x squared, well, the derivative of 3x squared is a 6x plus 2 times 1/2 of an x to the negative 1/2. And then we would subtract running out of space, 3x squared plus 2x to the 1/2 times the derivative of x, which is 1, all over x squared. My teachers told me to simplify at least combining of numbers. So I would call that x times 6x plus x to the negative 1/2 minus 3x squared plus 2x to the 1/2, all divided by x squared. But there's a different way. This is kind of a white-knuckle approach. We're taking the derivative of a quotient. We have a rule that allows us to take the derivative of a quotient. I applied the quotient rule. But 3x squared plus, and I'm going to go back to this form of the equation, 2x to the 1/2, all divided by x, well, that's equal to 3x squared over x plus 2x to the 1/2 over x, which is 3x plus 2 to the negative 1/2. So the derivative with regards to x of 3x squared plus 2x to the 1/2 over x, which we'd have to solve with a quotient rule, is equal to the derivative with regards to x of 3x, dropped my x there, plus 2x to the negative 1/2, which we don't even need the product rule. This is just the power rule over and over again. Derivative of 3x is equal to 3, to which we would add 2 times negative 1/2 of an x to a negative 3/2, or 3 minus x to the negative 3/2, which, if we were to algebraically manipulate what we have over here, would eventually reduce to this. X times 6x plus x to the negative 1/2 minus 3x squared plus 2x to the 1/2, all divided by an x squared. Well, that's equal to, multiplying that x in, 6x squared plus x to the 1/2 minus 3x squared plus, and then we will say 2x to the 1/2. All this is going to be divided by x squared, which is equal to 6x squared over x squared plus x to the 1/2 over x squared minus 3x squared over x squared plus 2x to the 1/2 over x squared, which is equal to 6 plus, that is going to be 1 over x to the 3/2, because we have 2 take away a half, minus 3 plus 2 over the same thing, x to the 3/2, which is equal to, there it is. I wonder if you guys caught it. By now, I like it when my class is screaming, "Teacher! Mr. Foley, you dropped your minus sign." Sorry about that. That minus sign got distributed to that 3x squared. That minus sign should have been distributed to that plus sign, which would make this plus sign a minus sign, which would make this plus sign a minus sign. Which now, when we gather like terms, 6 take away 3 is equal to 3. 1 over x to the 3 halves minus 2 over x to the 3 halves is a negative 1 over x to the 3 halves, or 3 minus x to the negative 3 halves. Okay, so you could have stopped here, or you could have stopped here. Taking a moment to breathe and look at the problem might make it so the calculus is a lot easier. Unless I specifically tell you, use the product rule or use the quotient rule, let me generalize that. Unless I tell you which rule to specifically use, I would always encourage you to look at the problem and see if you can make the problem a little bit easier. Always see if you can reduce it. If you can make the problem easier, go ahead and do so. Right now, I want to give you what I call our differentiation toolkit. This is what we have unlocked so far. I don't know why I've dotted a K. I gotta capitalize that K. We have the derivative with regards to x of any constant is equal to 0. We have the derivative with regards to x of any constant times some function of x. Constants can be pulled up and out, and this is equal to that constant times derivative with regards to x of f of x, which is that constant times f prime of x. Once again, whichever notation you prefer. The derivative with regards to x of the product is equal to the derivative of your first times your second plus your first times the derivative of your second. The derivative of the quotient is equal to low d high minus high d low all over low low. Or I've been writing this thing low d high minus high d low all over low low. We've got the derivative with regards to x of either the sum or the difference of f of x and g of x is equal to the sum or difference respectively of the derivatives. We've got a power rule. Oops, to the n minus 1. And the last one, we have the derivative of e to the x is just e to the x. These so far are the 1, 2, 3, 4, 5, 6, 7. We've got 7. You might consider that one too, because we've got one for addition and we've got one for subtraction. 7, 8 tools we have in our differentiation toolkit. These are your formulas. These are things that you should have memorized. You should be able to recall on command. You should, I just taught you these today, so you've got a while. But have these memorized. I don't do a lot of applications in my calc class because most of you are going to go off to some flavor of STEM that isn't necessarily mathematics, and all of those are primarily concerned with applications. So my goal is to get you guys to be able to take derivatives, so when you go to a statics class or a physical chemistry class or an economics class, you can take derivatives there. So your tools in your toolkit, go off and do for homework 3 through 23, every other odd. 27, 29, 41, 43. So like I said, the product rule and the quotient rule, they at a point should feel like muscle memory. It's a very plug and chug. You follow the formula, you put things where you go. After you've been doing it for a while, after it's no longer new to you, it should slowly become muscle memory. I gave you the every other odd from these sections so I didn't drown you in homework. If you need some practice with these, go ahead and do the other odds. And then where is this example? This example should illustrate something to you too, especially where we're at now. Mathematics is like a choose your own adventure book. You could either choose the quotient rule adventure, or you could choose the algebra plus the power rule adventure. These two answers were algebraically the same, but only one of these answers might be in the back of the book. It should be less concerning as you go forward in math when your answer does not match the answer in the back of the book immediately. You should be able to do some sort of algebraic manipulation to turn one into the other, but don't get discouraged when your answer doesn't immediately match. I'm more concerned with your work, which is why I have you stop at this step than try and getting the answer in the back of your book. But with that, like I said, go off and do this homework, and definitely I would highly recommend you making this page and keeping it close to you while you're going through this section. We're going to add some more tools to our toolkit as we progress through this chapter. But for now, these tools are at your disposal, and don't be afraid to manipulate a problem to make it easier for you. Have a nice day, everyone.